Okay, so last time we started talking about free groups. Let's keep going. So what we've done so far is the very first step, which is to construct the set of all words in the alphabet. So we're trying to find the free group in two generators, A and B. So we said let's look at words of S, which is just the set of all words formed using these two alphabets, and these look like this. There's the empty word, there's words of length 1, words of length 2, and so on. So it's an infinite set, and the important property was that this set had an associative operation, which we called concatenation of words, or putting two words together. So this operation was associative. And the other important fact is that it had an identity element, which is nothing but the empty word. But we realize that this set words of S with respect to this operation star does not have inverses. Okay, so it's not a group, and that's the thing that we'll try and remedy in today's lecture. Okay, so how do we make this a group? The first requirement for a group is inverses. And we notice that no element of this set has inverses except for the identity itself, which is its own inverse. None of the others have inverses. In particular, A and B, these two basic words of length 1, they don't have inverses. So let's try and construct inverses, or somehow introduce inverses. And to do this, there is sort of one key idea that we use. Okay, which is the following. Instead of looking at words in this alphabet S, we look at words in an augmented alphabet. Okay, so what does that mean? I'm going to enlarge the set S to make it somewhat bigger. There's A, B, and I'll put in two more elements, which I'll call A prime and B prime. These will eventually perform the role of the inverses. Okay, but for now, think of them as sort of two more alphabets, and we look at the set of all words in this 4-element alphabet. So that's still a very large set. It's now got all words in using A, B, A dash and B dash. It's got the empty word. It's still got an associative multiplication, and that associative multiplication still doesn't have inverses. Okay, so we have sort of just replaced the original set words of S by a much larger set in some sense. Okay, but here comes the key step. So we consider this. So that's step 1. Step 2 is really the key to everything that we are about to do, and this is a construction which will keep coming up in many places, which is the following. We impose the following relations. Okay, so we impose the following relations. What does that mean? Well, firstly, let me tell you what the relations are. So I want, look at the word A prime. This is a word of length 2 in words of S hat. This, I want to say that this word should be the same. Okay, so I'll just put the tilde there to say the same as or equivalent to the empty word. Okay, so I want to similarly make A prime A equivalent to the empty word. Okay, so I want to somehow impose these 4 relations. Okay, so notice that at the moment A, the things that I've written on the left hand side are all words of length 2, and of course on the right hand side we have the empty word of length 0, and of course these are not equal definitely right now, but what we want to do is to somehow say that we want to think of them as being equivalent. Okay, and not just this, we impose these relations, and further what else do we want to do? We also want to say that we can also replace. Okay, so here's sort of, think of these two steps right now as just being some sort of a heuristic idea of what it means for A prime and B prime to perform the roles of the inverses of A and B. So at the moment, don't think of them, don't be too worried about the lack of rigor, we will make it a little more precise soon. So heuristically, here's sort of what we want to do. We impose these relations, and what else do we also want? We also want to do the following. Whenever we have a word, say we have some long word in this alphabet a, b, a dash, b dash, and somewhere in the middle of this word, if I find any one of these four words of length 2, so for example something 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 a dash followed by a bunch of other letters, I want to be able to take this word and sort of remove the a dash from the middle. Okay, so I want to think of it as the same word in which the a dash block is removed from the middle, and then so I just take the words to the left of this block and concatenate it with the words to the right of this block. For example, so let's just do this by example. So I will go to the next page. So here is an example. So if I have, for example, a, b, b dash, a dash, a, b. Now look at this word. When I scan it, I notice that there is sort of this b, b dash which occurs one after the other. There's also another a dash, a which occurs one after the other. Okay, so in fact there are two reductions here that I would like to be able to do. So if a prime is to be the inverse of a, then we would want this word to be the same as or to be equivalent to the following word. So let me make the second a prime a into just the identity. So it just becomes this. And now I can look at this pair, or in fact if I choose I can also look at the other pair. Let's do the one in the middle. If I replace that with the empty word, then I want this to just collapse to the word AB. Okay, so this is one sort of reduction that I would want, which is what it means to say that a prime and a are inverses of each other, b prime and b are inverses of each other. So I mean, to take a maybe slightly different example, I can take a b, b prime, a prime, for example, and here again I would want to think of this word as being equivalent to the word a prime, and similarly the word a prime is equivalent to the empty word. Okay, so what exactly are we getting at this point? So this is really captured precisely by the notion of an equivalence relation. Okay, so if you sort of think a little bit about what we are doing, here's what it is. So what we want to do really is to define an equivalence relation so which I'll denote by tilde on the set of all words in the alphabet as at. Okay, so here's really what we are trying to do. Now the question is how to rigorously define such an equivalence relation. So we've already seen some of the requirements. We have those four important identifications. We would want these 5 words a prime, a prime a, b prime, b and the empty word to be equivalent to each other. Okay, so that is the primary requirement. And then the second property here is that whenever any of these occurs as a subword of a longer word, then inside that longer word you can replace the subword by any one of these other 4 subwords. Okay, so that's sort of what we want to do. So let's try and define this equivalence relation in a formal manner. Okay, so we say define. So here's the definition. Given 2 words W1 and W2, we say or we define W1 is equivalent to W2 if I can obtain W2, if W2 can be obtained from W1 by a sequence of what I'll call the basic rewriting rules. Okay, so let's see what is meant by this. So we've already seen an example of this just above. So what is a basic rewriting rule? Okay, and those are just the ones that we have talked about. So the basic rewriting rules are the following. So let me say, okay, so there are 8 basic rewriting rules. So what are the rewriting rules? It says, suppose I have a word. So if there is a word in which a prime occurs, okay, and there is something to the right. So this is maybe it's easier to call these two guys something. So let's call this whatever occurs to the left of a prime as the left subword L. So that's again a word in the alphabet, and what occurs to the right, so let's just delete the dots and call this as L, so some word, and what occurs to the right of a prime is R. So given a word of this form, some word L followed by a prime followed by some word R, I am allowed to rewrite. So this can be replaced with the word L R. Okay, in other words, I'm just going to delete the a prime from the middle. Similarly, if I have a word L followed by a prime A followed by R, again I'm allowed to replace that word with just the word LR. Okay, so let's write the other two. So when you get, so we say that the word LR is obtained from the original word L a prime R by using one of the basic rewriting rules. Okay, so these are called the basic rewriting rules, and these are 4 of them. Now there are 4 more which are just the same rules in reverse. Okay, so not only are you allowed to delete an a prime or an a prime a from a word, you're also allowed to introduce that if you want. Okay, so here are 4 rules, and the other 4 are just the reverses of the. So given 2 words L and R, I am allowed to introduce an a prime in the middle, or I am allowed to introduce okay, so I am allowed to replace LR with replaced with this with a word whose length is 2 more. Okay, so these are the 8 basic rewriting rules that I have. So what are the rewriting rules? They are a way of obtaining a new word from a given word. Okay, the first 4 rules give you a new word whose length is 2 less, and the next 4 rules give you a new word whose length is 2 more. Okay, now using any of these 8 basic rewriting rules in sequence, you are allowed to use them again and again, one after the other, in any order you want. Okay, now keep doing this, and starting from a word W, if W1, if you can somehow obtain W2. Okay, so going back to our definition, we said W1 is equivalent to W2. What does that mean? It means I start with W1. Okay, I see if one of these 8 rules can be obtained. I mean, can be applied. I mean, you can always apply one of the rules, because for example, the rules which allow you to add 2 letters in the middle, that can be applied to any word if you wish. So I take W1, I apply one of my basic rewriting rules, and it gives me some word. Okay, so I don't know, I should call it something. Maybe I get a word Z. What shall we call it? Z1. And I take this word Z1, I apply one other basic rewriting rule, maybe it gives me a word Z2, and on Z2 I apply one of the rules, I get Z3, etc., etc. And I keep doing this, say at some point I get Zk, and to Zk I finally apply a rule and it transforms into W2. Okay. So if you can do this, if you can find a sequence Z1, Z2, Zk such that this chain from W1 to W2 proceeds through successive basic rewriting rules, then you declare that W1 is equivalent to W2. Okay. So I hope the definition is clear. It's slightly involved. It's maybe not a kind of equivalence relation definition which you have seen before, but nevertheless, so the first order of business, let's check that this is actually an equivalence relation on the set. Okay, so let's check, is this an equivalence relation? Check that. Okay, so remember, equivalence relation means I need to check three things. I need to check that the relation is reflexive, which means given a word W, I need to check that it is equivalent to itself, and that is sort of trivial because I just don't apply any of the basic rewriting rules, right? I'm allowed to apply, any number of them, but I'm also allowed to apply just zero number of basic rewriting rules. In other words, I don't apply any rule. Or if you really wish to, to actually apply a rule, you can apply, for example, the say the fifth rule, and then follow it up by acting the first rule. Okay, so you add in the AA prime and then you delete the AA prime if you wish. So it's in fact a reflexive operation. Let's show the other two properties. Symmetry says that, so there's a second requirement of an equivalence relation is that it should be symmetric. So if W1 is equivalent to W2, then I need to show that this means W2 is equivalent to W1. Okay, but again observe, this is why we had 8 basic rewriting rules and not just the first 4. The rules 5 through 8 are just sort of the rules 1 through 4 in reverse, right? So if I have, say, some word W gives me a word X by using one of the basic rewriting rules. So let me say, if for example I apply rule 1 to go from W to X, then it's clear that I can get a W from X by just applying rule 5, right? If I can get this by deleting a pair AA prime, then I can get the other guy by just putting that pair back, right? Similarly, if I get a word X from W by applying, say, rule 2, then I can go back, I can undo it by using rule 6, etc. Okay, so it's clear that if I construct a chain going from W1 to W2, then by applying the rules in reverse, I can just get a chain going from X back to W. Okay, and third property, transitivity, is again as easy to check. Okay, so if I have a chain which connects W1 to W2, chain of rewriting rules, and I have a chain of rewriting rules connecting W2 to W3, all I have to do is just apply this first set of rules, follow it up by the next set of rules, and using that rewriting, I can start with W1, find a chain which takes me all the way to W3. Okay, so in fact, this somewhat strange definition defines an equivalence relation on the set words of S hat. Okay, so that's the first thing that we have checked. Okay, so now let's maybe just do an example of applying the sequence of rewriting rules and so on. So for instance, let me start with a word that has, say, A, B prime, B. Okay, so here's a word, okay, with A's, B's, A primes and B primes in it. And let me see what I can do by way of applying my rewriting rules. So I already see that there is a b prime b right there. So there are many other pairs which can be collapsed. For example, there's a b prime here, there is an a prime a there is an a prime a here, there is an a prime here, and so on. So I can of course apply my rewriting rules one at a time. So when I apply my rule, this guy becomes, for example, let me collapse the first pair. So this then becomes a prime, a prime a, b prime, a prime a. Or if instead of the first pair I choose to collapse the last pair, a prime a, so then that's like a b prime b, a prime, a prime a, b prime. Okay. Now so as you can see, you can keep going. So I apply, let's see, what shall we apply next? Suppose I collapse this a prime, then it becomes a prime a, b prime, a prime a. Then again here I have other choices. I could have collapsed let's see, maybe the next pair, a prime a, so that will give me a prime, b and so on. So this again, maybe I collapse the last b prime, a, and there's a b at the end, okay, and so on. So you can see that you will sort of form a structure like this, and of course it's an infinite set, the words you can get from a fixed word by using the rewriting rules, because I'm always allowed to add, you know, I can always insert an a prime or a prime a wherever I want. For example, I could take this original word, whatever it is, and maybe just take a prime a at the end. Okay, I just add one extra a prime a, okay, and so on. So you can imagine that it's like this. So some of these will eventually become the same, meaning this is and so on. Okay, and in this case, as you can probably see from what we underlined already, if you did the all possible collapsings to the maximum extent, I have b prime b is gone, a prime is gone, a prime a is gone, b prime is gone, this is gone. So finally, after all this, you will see that you will sort of get the word ab. Okay, so that's going to be a word which will eventually arise when you keep doing this, and in some sense that's the smallest words, the smallest, maybe you should call it the word of smallest length, or sometimes it's called the reduced word, and so on. But here's a nice exercise, you know, for you to play with. Just try to see what more, you know, try to write down a bunch of other words that you can construct, which can all be obtained one from the other by a sequence of rewriting rules. Okay, now our definition of the equivalence relation, what it says is that, for example, all the words that you see now on the page are all in fact equivalent to one another. Okay, why is that? Because no matter where I am, so for example, if I have this word here is actually equivalent to this word here. Okay, these two words are equivalent. Why? Because what does the definition say? I should be able to go from one to the other by applying one of my basic rewriting rules. So here's what I do. I first go up like this. Okay, so going from here to here involves insertion of a pair, a prime, and then from there I reach this word, which again was obtained by insertion, and then I go down like this, where this word is obtained from the word on top by deletion of some pair, and then I reach this point. Okay, so no matter where I am, I can always start there and reach any other point in this collection of words, either by using insertions or deletions of pairs a prime. Okay, so this entire collection is in fact equivalent. Everything here is equivalent to everything else, and this what we mean by an equivalence class is more or less this idea here. So recall that when I have an equivalence relation, so an equivalence relation always divides or partitions is the right word. An equivalence relation partitions the set, the underlying set, partitions the set into a collection of disjoint, into a collection of disjoint, what are called equivalence classes. So this is disjoint equivalence classes. Okay, so it partitions the set. In this case, the set itself is nothing but the set of all words. Okay, where what is an equivalence class? So here's, if you recall the definition, so suppose I pick a word W, I will denote by this square bracket W the equivalence class. So let's use this to denote the equivalence class to which W belongs. So this is the equivalence class of W, which by definition is just nothing but the set of all words X in the collection words of S hat, such that W is equivalent to X. Okay, so collect every other word which is equivalent, collect every word which is equivalent to W. That collection is called the equivalence class of W, and of course what this is a subset. This is a subset of the set of all words in S hat. Okay, and now here is the important definition for S. So let's call this set G is just the set of all equivalence classes. So G is the set of equivalence classes. Okay, for this equivalence relation tilde that we have just defined. So just take the collection of all equivalence classes. In other words, the elements of G are themselves subsets of words of S hat. Okay, now look at the collection of equivalence classes and observe that, so one way of writing it is to say it's the set of all W, as W varies over the set of all words in S hat. But note that, if I take an equivalence class of W, so W is sometimes, when we denote an equivalence class in this manner, what we are really doing is picking one representative W from that equivalence class. But note that the following is true: if I picked another element X from the same equivalence class, so I pick an element X from the equivalence class of W, then the equivalence class, so for all X in the equivalence class of W, the equivalence class of X is just the same as the equivalence class of W. Okay, in other words, the same equivalence class, in this case this, either of these two sides, they represent the same equivalence class, but the elements that you pick to represent it, which in this case are W and X, can very well be different. Okay, so that's something to always keep in mind when one is dealing with equivalence classes. Okay, now here's the very interesting observation that the way we have defined the equivalence relation, this collection G also has a well-defined, so G has a well-defined binary operation, basically a multiplication operation given by, so here's the definition. Remember, elements of G are themselves equivalence classes, so I take the equivalence class of W1, and here's this dot denotes the binary operation, the multiplication I'm going to define on G. So W1 times W2, the equivalence class, is defined to be, well, it should again be another equivalence class, and we just define it to be the equivalence class of the composition of W1 and W2. Okay, so observe the definition itself at the moment makes sense. I take two equivalence classes, W1 and I take two representatives, W1 and W2 from those classes. I concatenate those two representatives, I get a new word W1 star W2, and I take the equivalence class of that new word. Okay, that's my definition. Now the key thing that one needs to prove is really well definedness. Okay, the key point here is that this definition is well defined. And why does one need to worry about that? Because we are picking representatives from these classes W1 and W2. So it's not a priori clear that suppose I changed my representative. So here's what we will need to show. What if I pick different representatives? So if x1 is another representative, it belongs to this equivalence class, okay, and I pick a different representative x2 from the equivalence class W2, okay, then so what does that mean? I.e., I have, instead of taking W1 as my representative, I am thinking of x1 as my representative of that class, and similarly, okay, so I'm changing my representative. Then, so suppose I do this, then I need to show that my right hand side will be the same answer, whether I do W1 star W2 and take the concatenation, or I take x1 star x2 and take their concatenation, the answers should be the same. So okay, then we must show that x1 star x2, the equivalence class, is the same answer as what you would get if you took W1 star W2. Okay, so this is what showing well definedness means. Okay, so let's prove this. Again, it comes about from the special way in which the equivalence class or the equivalence relation was defined. So observe, what are we given? We are given that x1 and w1 are equivalent to each other. So let's prove this. Given, what's given is the following. These two are equivalent, and what we need to prove is that the concatenations are equivalent. x1 star x2 is equivalent to w1 star w2. Okay. So what does equivalent mean? It means there is a chain starting with w1 ending at x1, in which each intermediate step is obtained from the preceding one by an application of a basic rewriting rule. Okay. So let's write that down. So step 1, I start at w1, okay, and I use my basic rewriting rule. I get some word. I use again one of the other rules, it becomes some other word, etc., till I finally am able to reach x1. Okay, this is what it means to say w1 and x1 are equivalent to each other. Okay, similarly, I have w2 and x2. So I can start at w2, I can follow my rules successively till I reach, well, okay, so that's what the definition says. Now, given this, we need to show that if I start with w1 star w2, I can reach x1 star x2 by means of my basic rewriting rules. Okay, now the way we do this is just via this simple observation that look at this initial chain starting from w1 and going to x1. What does a basic rewriting rule do? The basic rewriting rule has the following form. So for instance, if this is my word w1, I look through the letters in w1, I either find a successive pair of the form a prime, etc., which I delete, or I take my word w1, I look through the letters, I pick some position, and there I insert a pair a prime. Okay, so the transformation that I perform has this very specific form. You either collapse or you sort of expand at a certain location in the word. So if I go from, let's look at the very first step of the chain, I go from w1 to whatever is the next word in the sequence by means of some basic rewriting rule, then here's what it means. It means that look at w1 and the next guy. Now to w1 on the right hand side, I can let me try doing this. Let me concatenate w1 on the right hand side with the word w2. Okay, and the next step in the chain I'll do the same thing to it. I concatenate W2 to that word. Now if this second guy can be obtained from the first one by some basic rewriting rule, then it follows that W1 star W2 will lead to that word star W2. Okay, I can take the second guy and I do W2 to it. So maybe I should give this a name. So this intermediate step, suppose I call it Z1, that's my word. Then here's what I mean, that if from W1 to Z1 I can go by means of a basic rewriting rule, I can also go from W1 star W2 to Z1 star W2 by the same rule really, okay, because I only need to apply that rule to the W1 portion of my word. Now and so on. So the next step again, because I can go from Z1 to the next fellow Z2 by means of some rule, it means I can also go from Z1 star W2 to Z2 star W2 by using the same rule but only applying it to the Z1 portion, and so on. Okay, so keep doing this till you reach the end. So the end here is x1, but of course remember I have starred every one of them with a W2. Okay, so I've started at W1 star W2, which is what I need to start with. Okay, so we have managed to go from W1 star W2, which is what we wanted, but we have only reached x1 star W2. Okay, but that's already a very good start, because now we do the same thing with the other sequence. We know that we can start at W2 and reach x1. So now let's do the same thing here. This implies now I will sort of concatenate on the left of W2. So starting at W2, I can reach the next step, whatever this word is. So let's call this Z1 dash. Now what I do is to concatenate x1 on the left of W2, and because I can go from W2 to Z1 dash, it also implies that I can go from x1 star W2 to x1 star Z1 dash in the same manner, and by the same logic as before. So I keep applying it to the next step of the chain and so on. So I keep doing this till I reach the very last step, and the last step is x2 but concatenated on the left by x1. Okay, so what this means is if I start at x1 star W2 by applying left concatenation to the second chain, I can reach x1 star x2. Okay, so now I just put these together. So what have I managed to do? I have managed to start at W1 star W2. I am following this chain of rewriting rules. So at this point, this and this are the same. Now I follow after that this chain of rules, and finally I reach my destination. Okay, so what this means is that W1 star W2 is in fact equivalent to x1 star x2. Okay, as required. So what this means is that my on my group G, or at the moment my set G, the binary operation that I have defined is, at least it makes sense, it's well defined. Okay, but we called it G for a reason. We are going to make this into a group. We are going to show that it actually becomes a group under this operation, and that's really our in some sense our main theorem. That's going to be the free group. So G is a group under the binary operation that we just defined. Okay, proof. Well, what all do we need to show? We need to show that the binary operation is associative. Okay, why is it associative? So we'll show that first. Observe the definition said if I take W1 multiplied by W2. Okay, let's just write out the definition of associativity here. This by definition is W1 star W2, the equivalence class of the concatenation, multiplied by the equivalence class of W3. Okay, which by definition again is the equivalence class of W1 star W2 star W3. Okay. But observe that what's inside the representative of the class that I get here is just the concatenation of these three guys, W1, W2 and W3, and the concatenation operation is of course associative. So I can replace this triple with say W1 star W2 W3, and that by the definition of the multiplication in G will just become this product, okay, and that's exactly the verification of associativity. Okay, now the identity is also easy. So there is an identity element. What should the identity element be? Well, so let's call it E, maybe the identity element of this group G. Well, I claim it's nothing but you take the equivalence class of the empty word. Okay, so that is the empty word in words of S hat. The equivalence class of the empty word, by the way, is it has lots and lots of words, remember, right? So we looked at A, for example, A prime, A prime A, those basic rewriting guys, they are all in fact in the equivalence class of the empty word. So this is in fact the set of all words which, if you keep applying rewriting rules, will finally come down to the empty word. The claim is that that serves as an identity, again by definition, because the multiplication just says for any word E, if I multiply it with the equivalence class of the empty word, I just have to concatenate W with the empty word, but that's just W. Okay, and observe the same logic holds in the other order. If I hit the equivalence class of the empty word with W on the right, then of course it gives me W. Okay. So in some sense, these two properties just follow from the corresponding properties of the star operation. So no surprises so far, but the reason we were doing all this is because the star doesn't admit inverses. Okay, but the important property here is that this does have inverses. Okay, in other words, it's a group. So let's verify this. Let's check that given any element of G, I can construct an inverse of that element with respect to this new operation that I have defined. So for a start, let's just look at the two basic generators A and B, the alphabets. If I just take the single, if I take the equivalence class of the word A, the question is, what is the inverse of this guy? So in other words, what equivalence class will you take such that, what should I put here so that this product gives me the identity element? And remember, the identity element just means it's the equivalence class of the empty word. Okay, and observe that, well, by definition, we already know something. So let's just throw that in. Let's perform a simple computation here. So observe, if I take A and I multiply it with the equivalence class of the element A prime, then by definition this is the equivalence class of the concatenation, the word A with A prime, which again by definition is just A prime, the word of length 2. But remember, A prime by the rewriting rule is the same as the empty word. Okay, so in other words, it says that A equivalence class multiplied by the equivalence class of A prime is in fact the identity element of this group. Okay, and of course in the other order as well, A prime multiplied by A would also give you identity. You can also check that the same is true of B and B prime. So this is what I meant when I said in the beginning that A prime and B prime will eventually perform the roles of the inverses. Okay, that's only, we have only constructed inverses for these special one letter words, if you wish. What about a general word? That's also very easy. So let's just do it by example, and you'll see the general picture very quickly. Suppose I take the word W equals A B B A, for example. Okay, so the question is, what should the inverse? So maybe I should make it slightly asymmetric. So let me put two A's on the end. So A B B A A, for example. Okay, so take this word W. I want to know what is the inverse of this word. Okay, so I claim here's a simple prescription. you just look at this string of letters, you read them in reverse. Okay, and when you read them in reverse, you just change all the A's to A primes and B's to B primes. So here's the prescription, the inverse of W, so let me call it W bar for now. This is just read W in reverse and replace any symbol that you see by its dash. Okay, so maybe I should call it replace each letter by its dash. Okay, so in other words, here I apply this prescription. I read this in reverse and I see two A's from the end, so I make them dashes. I make B's into dashes. So here's my claim is that this new word will serve as the inverse. So let us check. So how should we check? By definition, this product is just W concatenated with this new word, A prime, B prime, B prime, A prime, which as we know is A, B, B, A prime, B prime, B prime, A prime. So here's some long word, but I claim that if I keep applying my rewriting rules successively, I can convert this word into the empty word. Okay, so let's just do this sort of right there. So let me write down this word and I'll convert it into the empty word. So A, B, B, A dash, B dash, B dash, A dash. Okay, so let's just do it right there. So I have this pair A and A prime right over here. So I know that pair can be erased. I can make it into the identity, into the empty word. So I erase that from my word. Okay, now I look at what's left. Now again, in what's left, I see that an A and an A dash are paired up. So I can erase them. Okay, now I look at what's left. I see that this B and this B dash are paired up. So I erase them. Again, what's left? The B and this B dash are paired up. This A and this A dash are paired up. Okay, so you see that's exactly how we constructed the inverse. We just read the word in reverse, and for every symbol we just took its dash. Okay, and the reason for doing this is because exactly this sort of pairwise cancellation is going to happen. Okay, and in fact this was just a particular example, but more generally the word can have dashes as well. Okay, so here's here's another example. So if I have A, B, A dash, A for example, then I claim that the inverse of that equivalence class is just read the same thing in reverse but put dashes. If you see A, put an A dash. If you see an A dash, you convert that to an A. So that's it's in some sense A dash dash is like an A. So I claim it's this element. Okay, and I leave this for you to check. Okay, and it's easy to write a general prescription as well if you wish, that if W is a word which looks like x1, x2, xk, each xi is a letter, it's either A, B, A dash or B dash, then the inverse of W is just given by the equivalence class of, well, read it in reverse, so yk, and I change all the x's to y's, where what is yi is just the dash of xi. Okay, so just being a bit loose here, but you know what I mean. Each xi, if it's an A, then yi is A dash. If it's A dash, then it is an A. Okay, so what have we done? We have therefore proved that this group, so finally we have managed to do what we set out to do. We have constructed a group G with respect to this binary operation. So G with respect to this binary operation is called, so its definition, this is called the free group on the two symbols A and B. Okay, so observe it is it certainly contains in some sense the elements A and B, and next time we'll start looking at some of its other properties. Okay, for now at least the motivation for this terminology, I mean it's not yet fully clear, but we at least said let's start with A and B, let's not put any relations, just sort of let A and B be arbitrary symbols, let them generate, look at all possible products and so on. And in some sense what we did by this enlargement procedure is to say let's not just take products of A's and B's, let's sort of also take their inverses, let's also throw in two formal symbols which are like the inverses of A and B, and sort of take all possible products, all words with A in which A's, B's, A inverses and B inverses occur. Okay, and in some sense that's really what the free group is capturing. Okay, so more on this next time.